Today we're going to talk about Lagrange multipliers, which is a way of solving constrained optimization problems. That is, finding the maximum of a function when you're constrained to sit on a certain curve or a certain surface. But before we do that, let's talk about the unconstrained problem. Let's suppose that we have a function on the plane, here's R2, and we were trying to maximize a function f of xy. What I've drawn here is I've drawn the gradient of the function at various points. So if the gradient of the function here is given by this vector, could this possibly be a maximum? Well, no, because the gradient always points uphill, so you can always get a little bit higher by following the gradient. The gradient, and could it be a minimum? Well, no, because you could go the other way. You could go in the direction of the negative gradient and get smaller. So the only possible points where you could have a maximum or a minimum is where the gradient either doesn't exist or where the gradient is zero. And in this picture you see that if the arrows are pointing you uphill, this spot right there is going to be the top of the hill. And if the arrows point uphill, this is going to be the bottom of the valley. So this is going to be a local maximum and this is going to be a local minimum. You find the local maxima and minima by looking at the place where the gradient is zero. Okay, that's old hat. Let's look at what happens if you have a constrained problem. So we've got some function f of x, y, z, and we've got some surface. I'll call it the surface S. And the surface is defined by an equation. G of x, y, z is 0. So here's a picture. Here's our surface S. It's a torus with 2 holes in it. And it's given by an equation, g of x, y, z equals 0. And again, I've drawn in red the gradient of f at various points. Now, this is a surface in 3 dimensions, so the gradient is a 3-dimensional vector. It's not tangent to the surface, or at least it typically isn't. But at this point, it has a shadow. If you move in the direction of this vector here, then the dot product with the gradient is not going to be 0, and your function is going to increase. That means this can't be a maximum. If you move in the opposite direction, the dot product is again not 0, and your function value is going to decrease. It can't be a minimum. Likewise, at this point, that can't be a maximum or a minimum. In fact, the only possibilities, if the shadow of the gradient is non-zero, that always gives you a direction you can go to go uphill, and minus that, and going the other way will send you downhill. But now look at the point R. The point R is a point where the gradient is perpendicular to the surface. So no matter what direction you go, the dot product with the gradient is going to be 0. So to first order at least, you can't go uphill and you can't go downhill by following the gradient. The gradient is pointing you completely off the surface. Great. So we've learned that at a maximum or a minimum, the gradient must be perpendicular to the surface. Now what about the gradient of g? Well, the gradient of g, which I'll draw in black here, well, that's always perpendicular to the surface. This is the gradient of g. Why? Because as you move along the surface, g isn't changing. So the dot product with the gradient must be 0. So if the gradient of f is perpendicular to the surface, and the gradient of g is perpendicular to the surface, the gradient of f and the gradient of g must be pointing in the same direction. And that means that the gradient of f must be some number times the gradient of g. We use the Greek letter lambda to designate that number, and this number lambda is called a Lagrange multiplier. Why lambda? Because that's the Greek equivalent of L, and L stands for Lagrange. Okay? So let's do an example. let's try to maximize the function 3x plus 4y on the unit circle. Now, in this case, our function g, that's 0, isn't x squared plus y squared, it's x squared plus y squared minus 1. And computing its gradient is pretty easy. It's just 2x, 2y. And the gradient of f was 3x plus 4y. The gradient of that is just 3 comma 4. So we want to say that this must be a multiple of this. So let's look at what our equations are. Our equations say that 3, 4 has to be a multiple of 2x, 2y. So 3 is 2x times lambda. 4 is 2y times lambda. Take the ratio, or divide both sides by 2 lambda. X is 3 over 2 lambda, y is 4 over 2 lambda. Now we plug into our original equation, x squared plus y squared equals 1. And x squared plus y squared is 25 over 4 lambda squared. So that says 4 lambda squared is 25, which means that 2 lambda is either 5 or minus 5. This gives us 2 points. One where lambda is 2 lambda is 5, one where 2 lambda is minus 5. And in fact, at one of those points, the gradient is pointing straight out. That's our maximum. At the other point, the gradient is pointing straight in. That's our minimum. Okay, so there is the function. And how do you figure out what's a maximum and what's a minimum? Well, once you have your candidate points, you just plug in f of xy. You compute what f of xy is. In this case, it's 5. In this case, it's minus 5. So this must be the maximum. This must be the minimum. Finally, there's a funny thing about this whole game. When you think about a surface, you usually say this should be described by 2 variables. Well, we did a problem involving 4 variables. We used x, y, z, and lambda. And in fact, you can think of a big function, let's call it capital F, which is little f minus lambda times little g. And now it's a function not just of x, y, and z, it's also a function of lambda. If you take the 4-dimensional gradient of this big function, well, there are the 4 components. And you see that the first 3 components are just the gradient of f minus lambda times the gradient of g. So setting this 4-dimensional gradient equal to 0, it's the same thing as setting grad f equals lambda grad g, and setting g equals 0. In other words, we have to stay on the surface. We want points where the gradient of f is a multiple of the gradient of g, and we're on the surface. And looking at this function with one extra variable is a cute trick for doing that. And that is the theory of Lagrange multipliers.